Out in the freezing outskirts of a galaxy 750 million light-years away, a silent monster is drifting. A dormant supermassive black hole, weighing as much as 1,000,000 suns, is sliding through the dark void, completely invisible to our telescopes. This cosmic giant does not reside at the galactic center where it belongs. It wanders alone, a homeless orphan in the deep vacuum of space. For eons it remained hidden, a shadow among the stars. But in November 2025, this silent phantom crossed paths with a passing star. The star was pulled into its gravitational grip, torn apart, and shredded in a brilliant display of light that outshone its entire galaxy. This violent event, known as a tidal disruption, created a blinding flare of ultraviolet radiation. The cosmic light show radiated with the energy of 10 billion suns, announcing the presence of the hidden giant. Why was this black hole expelled from its home? How did a 1,000,000 solar mass object end up kicked into the galactic outskirts, wandering 30,000 light-years away from where it should be? And how did astronomers use artificial intelligence to detect this invisible predator in the dark? These questions challenge our understanding of galactic evolution and gravity. They force us to ask what happens when the largest objects in the universe are set loose. To solve this mystery, we must look back at a chaotic merger. We must examine the invisible forces that shape the destiny of galaxies. The answer lies in a violent collision that happened millions of years ago, a cosmic dance that ended in exile. This is the story of a wandering giant, a star-shredding beast that was caught in the act. As we trace its path, we uncover a hidden population of homeless black holes drifting throughout the cosmos, waiting in the dark. How many of these monsters are out there, and could one be heading toward us? To find out, astronomers had to build a new kind of trap, using advanced machine learning to scan the skies. The search for the wandering giant was about to begin, and the discoveries would rewrite the laws of cosmic history. Our journey into the shadows starts now, revealing a universe far more unstable than we ever dared to imagine. As we peer into this dark abyss, we must prepare to discard our old assumptions. Space is not a static canvas of quiet stars and predictable orbits, but a chaotic arena where giants can be cast out, wandering forever in the deep shadows. Imagine drifting alone for billions of years, 1,000,000 times heavier than our sun, with no light to guide you. This is the reality of the cosmic exile. As our telescopes scan the heavens, we are forced to confront a disturbing truth. The universe is littered with these silent monsters. We must find them, understand them, and prepare for what they reveal about the fate of our own galactic neighborhood in the dark. To find a silent killer in the dark, you must wait for it to eat. That is the lesson of the groundbreaking study published in July 2026 by astronomer Robert Stein and his team. For years, scientists assumed supermassive black holes only existed at the very center of galaxies, locked in place by gravity. But this discovery shattered that assumption. It proved that massive black holes can wander the galactic outskirts, completely invisible because they are dormant. Under normal circumstances, a quiet black hole emits no light, leaving no trace of its presence. It remains a cold, silent phantom, hidden against the blackness of empty space. But when an active telescope survey scans the sky, it looks for transient events, sudden fleeting flashes of light that signal cosmic violence. The Zwicky Transient Facility at the Palomar Observatory in California is one of these surveys. It scans the night sky, generating 500,000 transient alerts every single night. The telescope captures millions of stars, searching for any sudden change in brightness. No human team of astronomers could ever filter through this overwhelming flood of data to find a single star-shredding event. That is why the research team developed a custom artificial intelligence algorithm. This neural network was trained on thousands of simulated light curves, learning to recognize the specific signature of a tidal disruption event. In November 2025, the algorithm flagged an unusual flare in the outer regions of a distant galaxy. It was located 30,000 light-years from the core of WISEA J0146-1522. The AI detected the flare immediately, prompting astronomers to trigger follow-up observations with ground and space instruments. Using the SOAR telescope in Chile and NASA's Neil Gehrels Swift Observatory, they confirmed the nature of the event. The spectra revealed a 1,000,000 solar mass black hole devouring a star, proving the existence of a wandering giant. The AI had caught the silent predator in the act, opening a new era of cosmic hunting. The host galaxy itself is a massive stellar system, and this specific star-shredding event was cataloged as TDE 2025 BCR. By using machine learning, the researchers could bypass the limitations of human observation, allowing the AI to scan millions of candidate alerts in seconds. The algorithm operates 24 hours a day, filtering noise from cosmic rays and normal variable stars to pinpoint the signature of tidal disruption. When it flagged the flare, the coordinate data was sent to international telescope networks within minutes. This rapid response allowed astronomers to capture the critical early stages of the star's destruction. Without this intelligent automation, the wandering giant would have remained completely hidden, drifting silently forever in the dark cosmic outskirts. This single event proves that transient astronomy is undergoing a profound revolution, where machine learning acts as our eyes, finding active anomalies that human eyes would completely miss. It is only the beginning of a larger campaign to map the dark side of the mysterious cosmos. But the most terrifying part of this discovery is not the event itself, but what it reveals about the very space we inhabit. If a giant black hole can be cast out of its galactic home, then no corner of the cosmos is truly safe. How do you launch a million solar mass monster? To answer this, we must first understand the physics of the crime scene. When a star wanders too close to a black hole, it crosses a critical threshold known as the tidal disruption radius. Here, the gravitational force exerted by the black hole on the near side of the star is vastly stronger than the force on the far side. This difference in gravity, known as a tidal force, quickly exceeds the star's own self-gravity. In an instant, the star loses its spherical shape and is stretched into a long, thin stream of hot gas. Physicists call this violent process spaghettification. Half of the stellar debris is launched into space on high-speed trajectories, escaping the black hole's grip. But the other half is bound to the black hole, falling backward in elliptical orbits. As this returning gas collides with itself, it forms a rapidly rotating accretion disk around the event horizon. The intense friction and gravitational compression heat the gas to millions of degrees, causing it to glow brilliantly in ultraviolet and X-ray wavelengths. This creates the ultra-bright flare captured by our telescopes, radiating with the light of 10 billion suns. The Neil Gehrels Swift Observatory tracked this fading light curve, confirming that the gas was indeed spiraling into a supermassive singularity. This stellar death is a slow process, taking months to complete as the black hole slowly devours the remains of its victim. Every second, the event horizon swallows a mass equivalent to entire oceans, releasing energy that shapes the host galaxy. This process is a rare window into general relativity, allowing us to observe space and time warped to the absolute limit. By analyzing this extreme emission, physicists can calculate the black hole's mass, spin, and the composition of the doomed star. The star-shredding event is not just a destructive display. It is a cosmic laboratory, revealing the extreme mechanics of gravity in regions where humans can never go. But how did this giant get here? To explain its presence in the outskirts, we must look beyond the physics of individual stars. We must examine the colossal forces of galactic collisions where entire worlds are thrown into exile. When entire galaxies merge, the gravitational disruptions are so immense that they can easily alter the trajectory of supermassive black holes, pushing them far from their stable positions. This is not a gentle process, but a violent reorganization of gaseous matter on a scale that defies human comprehension. The resulting recoil is a testament to the chaotic power that drives the evolution of our universe. As we investigate this exile, we discover that very space is far less permanent than we once assumed. How do you kick a million solar mass black hole out of its galactic home? The answer requires a force of unimaginable scale, a cosmic collision that reshapes space and time. Astronomers believe that wandering black holes are the direct result of galactic mergers. When two massive galaxies collide, their central black holes are drawn together by gravity. They begin an orbital dance, spiraling closer and closer over millions of years. As they rotate, they emit gravitational waves, ripples in the fabric of space-time itself. But these mergers are rarely symmetrical. If one black hole is larger, or if they spin at different rates, the gravitational waves are emitted unevenly. This creates an asymmetric release of energy. When the two black holes finally merge into one, the uneven gravitational waves deliver a massive momentum recoil. This recoil, known as a gravitational kick, acts like a rocket engine. It launches the newly merged supermassive black hole out of the galactic core. The kick can reach speeds of hundreds of kilometers per second, sending the giant flying into the outskirts. This is the birth of a wandering black hole, an orphan stripped of its home. But this process raises a profound scientific paradox. Will this kick giant ever return to the galactic center, or is it doomed to wander the void forever? The physics of this recoil are still hotly debated in the scientific community. Some theoretical models suggest that gas drag and dynamical friction will slowly pull the black hole back to the core over billions of years. Other models indicate that the kick can be strong enough to eject the black hole entirely, casting it into the empty space between galaxies. This debate highlights the limits of our understanding of gravity and galactic evolution. The wandering giant we detected is a living laboratory, a test case that could resolve these fundamental questions. It challenges our neat models of cosmic order, proving that galactic mergers are far more violent and unpredictable than we ever imagined. To calculate the velocity of such a kick, astrophysicists used complex simulations of general relativity. Solving Einstein's field equations under extreme conditions, they find that the speed depends heavily on the ratio of the black hole masses and the alignment of their spins before the final merger. If the spins are aligned in opposite directions, the resulting asymmetry is maximized, producing a recoil velocity that can exceed 1,000 kilometers per second. This is fast enough to escape the gravitational pull of smaller galaxies entirely, turning the merged singularity into an intergalactic wanderer. In larger host galaxies, however, the black hole remains bound but is thrown into a highly eccentric orbit that takes it far into the halo. As it travels through this dilute gas, it experiences dynamical friction, a gravitational drag force that slowly robs the giant of its kinetic energy, pulling it back to the core over billions of years. This orbital balance determines if the exile is permanent or temporary. The discovery of the wandering giant in WISEA J0146-1522 is not just an isolated anomaly. It is the first proof of a hidden population of orphan black holes drifting through the cosmos. Astronomers estimate that there could be thousands of these invisible monsters wandering the outskirts of galaxies across the universe. Until now, they remained completely undetected, quiet phantoms hiding in the dark. But with AI-powered surveys, we can now hunt them down, using their star-shredding meals to reveal their locations. This AI-assisted technique is a paradigm shift, allowing us to map the invisible dark matter of the universe. It suggests that galactic outskirts are not quiet deserts, but are instead filled with silent predators. This realization brings the mystery much closer to home. If wandering black holes are common throughout the universe, what about our own Milky Way? Our galaxy has a history of collisions, having merged with smaller galaxies in its past. Could there be dormant, supermassive black holes wandering the outer arms of our galaxy, perhaps even near our solar system? These silent giants would be completely invisible, detected only if they shred a passing star or planet. The thought is both terrifying and humbling, reminding us of our fragile place in a chaotic universe. Robert Stein's team has shown us that the sky is filled with secrets waiting to be uncovered by the union of human curiosity and artificial intelligence. As we look up at the night sky, we must accept that the dark void is not empty. It is a playground of homeless giants quietly drifting in the cold. We are only beginning to map this dark census, and the search has just started. To stay updated on this cosmic hunt and other space discoveries, subscribe to the channel and leave a comment below. Do you think a wandering black hole could be passing near our solar system? Tell us your thoughts and join us on this journey into the unknown. In the coming years, new observatories like the Vera C. Rubin Observatory in Chile will begin operation, scanning the entire visible sky every few nights with a massive 3 billion pixel camera. This telescope is expected to detect thousands of new transient events, including many more tidal disruptions in the outskirts of distant galaxies. At the same time, NASA's Nancy Grace Roman Space Telescope will search the deep universe for the infrared signatures of these dormant monsters. These advanced technologies will allow us to conduct a systematic census of the dark universe, transforming our understanding of black hole populations. They will turn our theories into verified maps, showing us where these silent predators lurk. As we map these invisible giants, we are reminded that our solar system is a tiny protected oasis in a vast, wild cosmos. The discovery is a reminder that we are travelers in a restless universe where even the largest objects are in motion. Each new telescope will help us chart this dangerous and beautiful cosmic wilderness.